Hi everyone. All right, so here's our video lecture for Chapter 5 for Z-scores that you should be watching at home because of the cold weather. Just a reminder, remember that you have to have worksheets 4 and 5 done by next Tuesday, which I think is the 5th. So come to class with both worksheets completed, and I'll collect those. So in other words, we're remaining on schedule here because we've got to make sure that we cover absolutely everything through Chi-Square. So we can't really take away a lecture and just sort of move things down today. Okay, cool. Let's just get right into this. Kind of weird to do this without anybody in front of me, but okay. So as you guys know, I've collected data from previous classes about, how stressed you think you'd be, what your GPA is, so on and so forth. One of the things that I also used to ask at the beginning of the semester was on average, how many texts do you send per day? And so here I have data from two students, right, about their texting behavior. Student X sends 30 texts, and student Y sends 200, right? So to interpret these numbers, right, 30 and 200, so what piece of information might be helpful? Well, the mean might be helpful, might sort of be useful to know, how many texts per day on average the class sends, and sort of use that as a comparison point between individual students and sort of the group average. And so in this case, the mean is 106, right? There's 106 text messages per day, which seems like quite a bit, but I'm not judging. So given this mean of 106, we might ask ourselves, well, does student X test a lot or too little compared to the mean? What about student Y, right? I mean, 30 is less than 106, 200 is greater than 106. We might ask ourselves, is it pretty extreme compared to the mean, or is it relatively close? It's just hard to say by comparing a raw score with just the mean, right? Where there's more information we need. So there's something else that might be helpful. It might be a measure of variability. So for example, the standard deviation. And I've already calculated that as well. And here you can see the standard deviation is 195. And so remember, the standard deviation indicates the typical deviation from the mean. So on average, the number of text messages people send is about 195 text messages away from the mean of 106. So now if we're given the standard deviation, we can see that even though 30 is much less than the mean of 106, it isn't exactly extreme, right? It's within the typical deviation. And what about student Y, right, who sends 200 text messages? It's the same story, right? It's also worth noting that we're taking two fairly extreme observations, I guess one could say, right? And it's important to note that this distribution that these scores are being taken from isn't very normal, right? As you can see here on this slide, I've posted a histogram from SPSS for all the text messages, right? You can see the skew here, right? It's fairly positive, or not fairly positive. It's a positive skew. Most people are down in the sort of 0 to 200 range, but there's a few people who are much higher, right? Somebody has sends a really large number of texts, as you can see, sort of skewing off to the right there. So what should be obvious here is that the influence of outliers, sort of when it comes to interpreting these data. So I can get rid of a handful of observations, right? I could say, well, again, I'm sort of arbitrarily doing this. It isn't sort of the way we would typically do it, but I'm just doing this as an example. I can get rid of observations that are above 500, right? And now I can look at this and note here in the, I'll use this today, in the corner there, I have the new standard deviation and the new mean once I get rid of those extreme observations above 500. And so now I can ask myself, is 30 still an extreme score? And if we look at the mean compared to the standard deviation, right, you imagine backing the standard deviation out of that mean, we'd still say no, right? It's still within one standard deviation, but what about 200? Well, all of a sudden, 200 becomes quite an extreme score, right? Because if we took the mean and added standard deviation to that, it's roughly somewhere between 2 and 3 standard deviations above the mean. It's somewhere in that range. So now 200 texts would certainly be considered an extreme score, right? So you can see, and we still have, positively skewed distribution, but once we get rid of those outliers, it's a little bit easier to interpret. This slide is sort of just for fun to see how my classes have compared with sort of the national average for 18 to 24-year-olds. And this is data taken from the Pew Research Group from 2013. I'm sure it's changed a bit, but not sure how much, but it's still sort of applicable. We get a sense of sort of how people in the age range of 18 to 24 with text compared to other groups. And remember, our mean was 106, right? Which it seems a bit higher in general compared to the population data itself, but fairly. If you look at the 18 to 24-year-old range of text daily, it's 128, right? So most students in college are around the typical average of 18 to 24-year-olds in the United States. Okay, so getting back on track here, the textbook uses some familiar examples of text scores test scores. So imagine you get a 76 on an exam. You might ask yourself, is this good or bad? Right? We all have our own individual standards, but it also depends on the class, right? In some cases, getting the 76 would be a pretty high score in relation to what everybody else got, but in others it might be about average. Some classes, a score of 76 out of 100 might seem relatively low compared to the performance of the rest of the class. For what it's worth, in this class, somewhere in the mid-70s is kind of typical for the average exam scores, right? Maybe it's 76 would be a little low for everybody's sort of average grade, final grade by the end of the semester. So just as it was with the text message example, sort of knowing the mean and standard deviation certainly helps put this score into perspective. So with a mean of 70 and a standard deviation of 3, that's what's going on in the top part of this figure. Well, 76 would be a really good score, right? You'd be sort of towards the top of the class. But if you look at the bottom figure where scores are much more spread out, with a mean of 70 and a standard deviation of 12, 76 sort of falls in the range of average, but not by much, roughly about sort of a half of standard deviation above a mean, right? So the take-home message here is in order to interpret any particular score, it's helpful to understand where that score lies within the distribution, right? How does it compare to the mean? And a useful way to make this comparison is thinking about your scores in terms of standard deviations. So the first exam is coming up fairly soon. I think we're, almost a week away or something like that. And so imagine you get 81 out of 100 points on that exam. So you have a raw score of 81. Now you can use the mean and standard deviation of a distribution to transform a raw score into what we call a z-score, right? And so z-scores have two important functions. They describe the location of where the score falls in the distribution. And it also allows us to compare one score with another in terms of standard deviations, but it also allows us to compare, say, scores on the exam, the raw score that you got in exam. I can compare that with raw scores on previous exams, right? So I can do these comparisons by standardizing everybody's score and compare them across years. So a couple of key points here. Rather than just knowing that the raw score on the exams is 81, we're going to have a precise understanding of how that raw score compares to everybody else who took the exam. So that is, we're going to know the location of that score relative to all of the other scores in the distribution. So again, imagine your first exam score. It's and there's another way of thinking about this too, right? And the idea of comparison, right? This is a critical sort of idea to wrap your head around. So you get this 81 out of 100 on the exam. Maybe if you add up all of the points of your first three worksheets, you get 33 out of 45. And you might ask yourself, like, okay, well, what am I doing better on? Am I doing better on the exams, or am I doing better on the worksheets? And here's the deal, right? We can't actually compare these raw scores directly because they're on different scales, right? The exam's out of 100. If you were to add up the total of your first 3 worksheets, that's out of 45, right? So they're different scales. So in order to compare them, and we can use z-scores to do this, we have to standardize them, right? And we can do this by putting them on the same scale. Now, one thing we could do is we could convert each of your 3 homeworks combined and separately your exam score. You can convert that to a percent, but it doesn't let you know how you're doing compared to others, which is as we saw sort of in the previous few slides, can be very helpful. So instead, we can convert each raw score into a z-score, and that's going to show you how your relative performance on the exam compares to your relative performance on the first 3 homework worksheets. Now, we're going to start off by talking about the first function, right? And then we're going to come back to this idea of comparing across distributions after that. Okay. So now I'm going to talk about this idea, the first sort of concept. The standardization process gives us the relative position of each score, okay? So first thing I want to draw your attention to is there's always a plus or minus sign in front of the z-score. And that z-score sign indicates whether the raw score, the x, right, as we'll refer to it, is above or below the mean, right? So plus if it's above the mean, minus if it's below the mean, right? Now, the z-score value, the numeric value, will tell us how far above or below the mean that score is. So this is just an idea to commit to memory, right? A z-score is always positive or negative. And when you're doing the worksheets, when you're doing the exams, don't forget the sign, right? A z-score is always positive or negative. Positive or negative denotes whether it's above or below the mean. The actual score value indicates the distance between the raw score and the mean in terms of the number of standard deviation units, right? So here's an example, right? Let's say there's a z-score of -1, right? That means the raw score is 1 standard deviation below the mean. So let's pretend in this example that the real standard deviation is 6, right? Then this raw score, right, if you have a z-score of -1, then your raw score is 6 points below the mean. So remember, the standard deviation, it's the average distance from the mean. So this score would be pretty typical, right? Nothing too extreme. It's within 1 standard deviation below the mean. Okay. So on the exam, you're going to need to be able to interpret the z-scores by saying whether a person has scored higher or lower than the mean, and by how far, right? So here's an example, right? Say you have an exam score that's 3 standard deviations above the mean, right? So it's 3 standard deviations above, so z equals +3, 3 standard deviations above the mean. And you might wonder, well, is this much better, slightly better than the typical student? Well, this would be much better than the typical student, right? Because 3 standard deviations above the mean, is quite an impressive performance, right? So you should be able to sort of look at these z-scores, look at the sign, look at the value of the score, and get a sense of, how good performance is in that z-score related to sort of a typical average performance. And sort of as another idea here to wrap your head around is, what would be the z-score for the mean exam? Or the mean exam score, sorry. Think about it for a second. It would be 0, right? Remember that the z-score tells you how many standard deviations away from the mean, right? It is, right? Well, the mean of 0 is in this case, the mean is 0 standard deviations away from itself, right? So the z-score for the mean would be 0 because there's no such thing as a variance away from sort of the mean in that sense. This figure should make things a little bit more intuitive. So Again, the z-score for the mean is always going to be 0, right? We never really talk about it in terms of that sense. But a z-score of +1, right? A z-score of +1 indicates that your one standard deviation, that's kind of messy. I hate writing with this pen. One standard deviation above the mean. A z-score of -2, right? A z-score of -2 indicates that you're 2 standard deviations below the mean. Now, it doesn't matter what the mean is, and it doesn't matter what the standard deviation is. We're sort of talking about these in terms of just what the raw score's location is in terms of a z distribution. So on the top distribution here, we have a raw score of 76, right? And that would be 2 standard deviations, right? Because the standard deviation here is 3, right? We've got it right there. A raw score of 76 with a mean of 70, right, is 2 standard deviations above the mean. Where in the bottom distribution, a raw score of 76, right, is roughly half a standard deviation above the mean, right? Because it's 6 points above. The standard deviation is 12, so half of that would be 6 points, right? So you should be able to sort of look at these distributions, look at these z-scores. If you knew the mean and standard deviation, you should be able to say in the exact units of standard deviation measurement, like how far above or below the raw score is from the mean. Now, calculating the z-scores is very easy, right? It's simple to do. This is the formula right here. So you're going to take the raw score, subtract the mean from that, and divide it by the standard deviation. And we're going to do a couple of examples here. You can also, if you knew the mean and the standard deviation and the z-score, you could calculate the original raw score value by simply multiplying the z-score by the standard deviation and just adding that to the mean. So these are the 2 equations that we're going to be working with today and on the worksheet as well. So again, to calculate the actual z-score, you'll need a raw score, the mean for all your scores, and the standard deviation for all your scores. And if you didn't have the raw score, if you were asked to find the raw score, as long as you had the mean, the z-score, and the standard deviation, you could use that information to find out what that score is. All right. So here we have one of our people from a previous class. We've picked on this person for quite some time. They had said they expected to have an anticipated stress score of 8 for the semester, right? So we have this raw score of 8. We have a mean for everybody of 73.9, and already computed the standard deviation for that class, and it was 17.71. So we can use this information to compute a z-score. We can say exactly where on the distribution, how many standard deviations a raw score of 8 is from the mean. And so I'm going to draw off my pen here. It doesn't always work very well, but I'll give it a shot. I apologize if it looks kind of messy. But remember, our formula, so we're going to find the z-score here. So it's going to be the raw score minus the mean divided by the standard deviation. So our raw score is 8. Our mean is 73.9. And we're going to divide that by 17.71, right? So I've got my calculator here. So 8 minus 73.9, 8 minus 73.9, that's going to give us negative 65.9, and we're going to divide that by the standard deviation of 17.71. And we get a z-score, right? I'll write this in here. Again, I apologize for how cruddy it looks, of negative 3.72. Yeah, I get 3.72106. So if we round it to 2 places, it would be a z-score of negative 3.72, right? So a raw score of 8 is almost 4 standard deviations below the mean, right? It's exactly 3.72 standard deviations below the mean. So it's quite an extreme score. Now remember, I want to sort of draw your attention that, if you look at the homework and get used to this idea, because it's going to constantly ask you to plot these normal distributions like you see here and label where your scores are. And I don't know, like, somewhere around here, I don't know, give or take right around here. Not a very straight line, I apologize, but that's somewhere probably where negative 3.72 is. So you would want to draw a distribution like what you see on this slide. Make sure you label the mean and make sure that you label your z-score, right? So, you can get a visual sense too of how far away that score is from the mean. So this is pertinent to one of the questions on the homework, right? You're going to be given a z-score and asked to find the raw score, right? And here's how you do it, right? You're going to take the mean and well, actually, first you would multiply the z-score by the standard deviation and simply add that to the mean, and that'll give you the exact raw score, right? So here, what we're asking ourselves is, okay, let's say somebody had a z-score of 0.18 plus 0.18. What is their raw score, right? And we can find that very easily, right? So first I'm going to multiply 0.1, it's more like a slash. I'm going to multiply 0.18 times our z-score, our standard deviation rather, of 17.71, and we're going to add that to our mean of 73.9. Right, so let's do that right now. So 0.18 times the standard deviation of 17.71. That gives us 3.1878, and I'll just add our mean of 73.9 to that. And so we get 77.08. I'll just round that to 77. So somebody that had a z-score, right, of 0.18 had a raw score of 77. Okay, so here's where I would typically ask if you have any questions, but since we're watching this at home and doing this at home, no such luck. But remember, if you after you've watched the lecture, after you've read the chapter, if you have any questions, feel free to bring those with you to class. All right. So this is very similar to one of the problems you have to do on the worksheet, right? So the day after performing a novel motor task in a lab, a non-athlete and skilled athlete perform an additional task to see how well the previous task generalized to the second. So in other words, the researcher are asking, okay, they did this one task. Did it help them on the second task, right? Or as a consequence of learning how to do the first novel task, does it help them to do the second one? And so a non-athlete got a score of 63, a skilled athlete got a score of 59. And also you see here the distributions for these two groups, right? So the mean for the non-athlete group was 60 with a standard deviation of 6, and the mean for the athlete group was 55 with a standard deviation of 4. And what we're asking here is who showed better improvement on the second task? Now, because we're interested in generalizability between the two tasks in relation to sort of athletic skill, we can't really directly compare the raw scores of 63 and 59 because these scores come from different distributions. Is that clear? Right? So the non-athlete group had a mean of 60 with a standard deviation of 6, and the athlete group had a mean of 55 with a standard deviation of 4. And so each one of these raw scores, 63 and 59 respectively, each one came from a different distribution. So you can't just say, well, the non-athletes got 63, the skilled athletes got 59, so clearly the non-athletes did better. You can't just say that on face value. You have to take into consideration where each one of these people performed relative to the performance of their overall group, right? Where their score fit in to the distribution, right? So in order to meaningfully compare these two scores, we need to standardize each score. So we need to convert the two raw scores into z-scores that we can compare their individual z-scores and take into consideration their performance relative to the rest of the group. Take a stab at sort of doing that on your own. You can always pause the video and I'll come back and work through the example on the next slide. Okay, so in this example, the non-athlete had a raw score of 63, right? And the population mean for non-athletes was 60 with a standard deviation of 6. So again, I'll just write it in here in my cruddy pen. But what we're going to do is just figure out the z-scores for each group, right? So we're going to start with a raw score of 63. Oh, that's not going to come out. That's weird. Why did that stick on there? Oh, whatever. A raw score of 63, right? So x minus the mean divided by the standard deviation, right? So 63 minus 60 is 3, right? So 3 divided by 6, that's going to give us a z-score of positive 0.5, right? Or 0.50, because you got to report it out to 2 places. And then let's look at the athlete group, right? So they had this particular person had a raw score of 59 minus the mean of 55 divided by a standard deviation of 4, right? So let's see, 4. Well, that's going to be 4 divided by 4. So that's going to give us a z-score of plus 1. Okay. So then remember, we're going to want to plot these scores on a normal distribution, right? So here's our scores. Here's our distribution. So the non-athlete with a z-score of 0.5 is somewhere around here, right? So we go plus 0.50, and then our other one is around a standard deviation of plus 1. Okay. So let me get to the next slide here. The non-athlete had a z-score of plus 0.5. The skilled athlete had a z-score of plus 1, right? Who showed better improvement on the second task, right? So the skilled athlete did. Even though their overall score was lower than the non-athlete, their raw score. Remember, the non-athlete got a 63, the skilled athlete got a 59. Given their performance within the distribution that they came from, right? Accounting for the fact that the non-athlete that got a score of 63 came from a distribution with a mean of 60 and a standard deviation of 6. Given that the skilled athlete got a raw score of 59, but that mean of that distribution was 55 with a standard deviation of 4, right? So given the performance of their distribution, the skilled athlete actually showed the greater improvement between the two tasks, right? So I told you at the beginning, converting scores to z-scores has 2 purposes: finding the location and comparison. We did a little bit of comparison work there, but we can sort of take it kind of to a higher level, right? We're going to move on to discussing not just a single standardized score, but an entire distribution of standardized scores. And so there's a question on the worksheet. It first might seem like a tough conceptual question, right? But it's really not that difficult. It presents a scenario where you're going to have an overall group mean and a standard deviation, and it picks one person out of the sample and gives you their z-score, right? So it's going to tell you where they fit into the distribution, and then it asks, okay, what does this mean in the real world? And we can sort of think about this for a second. We can use the group means and standard deviations for our non-athletes and our athletes, as well as the raw scores for the 2 people from each group that we had sort of picked out for the last problem. So remember, the z-scores have something to say about where someone falls in the distribution. So how many points did people differ from their group mean? How many actual points? All right. So to figure this out, you can multiply the z-score by the standard deviation that it came from, right? And so sort of as a side question while we're here, this sort of relates to the question on the homework, which we can look at these data, right, for these 2 raw scores as they fall in their distribution, ask, well, which person performed closer to their respective mean? Okay, well, the non-athletes had a z-score of plus 0.5. The athlete had a z-score of plus 1. So clearly the non-athlete was within half a standard deviation of their mean. The athlete was within a standard deviation of their mean. So the non-athlete actually performed closer to their mean, right? So the person who performs closest to the mean is going to be more typical, right? Because they're closer to the average. Whereas if one of these people had a really large z-score, then they wouldn't be very representative of the typical performance because their performance would be so far from the mean. Okay, but sort of I've gone off in a different direction here. The question I'm asking is how many points is the non-athlete and the athlete away from the mean? And like I said, you can get that by multiplying the z-score by the standard deviation. So for the non-athlete group, we can take that z-score of 0.50 or 0.5, and we can multiply that by the standard deviation of 6. And we get a 3, right? So half a standard deviation is 3 points, right? So the non-athlete scored 3 points higher than the standard deviation of their distribution. And you can do the same thing for the athlete, right? Well, so you have a z-score of 1, right, or 1.00. If you multiply that by the standard deviation of that distribution, very easy to do, you're going to get a 4. So the athlete scored 4 points higher than the mean of their particular distribution. So you can use the z-score and the standard deviation to find out exactly how many points somebody performed away from the mean, right? Okay. So a standardized distribution is a distribution where all of the raw scores have been transformed into new values in order to create a predetermined mean and a standard deviation, right? So an example of this is a distribution of z-scores. So if every x value for an entire distribution is transformed into a z-score, then the resulting distribution is going to have some very specific properties, right? First of all, it's going to maintain the shape of the raw score distribution. So individual locations within the distribution aren't going to change, right? If the raw scores were negatively skewed and we converted every single raw score into a z-score, the distribution of z-scores is also going to be negatively skewed. The mean of all z-scores is going to be 0, right? We learned that sort of earlier on, right? The mean has a z-score of 0. It's the same thing. And the standard deviation of all z-scores is going to be 1. So a distribution of z-scores is an example of a standard distribution, right? All of the scores are transformed so that there's a set mean and a set standard deviation. All z-score distributions have a mean of 0 and a standard deviation of 1. And so z-scores are actually easier to work with than raw scores, but they still have decimals and negative numbers, which can be confusing for people, especially once we get sort of outside the classroom or research setting, right? And so to deal with this problem, we can use z-score distributions to create other simpler standardized distributions, right? And so in order to do this, right, and I'll talk about this more over the sort of next few slides here, but in order to do this, we create a standardized distribution. We're going to transform the raw scores into z-scores, right? So we're going to take a raw score, take that distribution, turn it into z-scores. Then we're going to transform this z-score that we've computed into new raw scores, fitting a new distribution that we've created, right? That's going to have its own mean and its own standard deviation, right? And this is done all the time. Particularly, it's done in sort of standardized testing for things like the SAT, because, you know, occasionally they'll change things like SAT and GRE, and they still want to be able to compare performance across years, right? So here I have an example of the SAT from 2016. And so just a little bit of background here. On the SAT, the raw score is calculated based on the number of questions that you answer correctly, right? And the number of questions that you answer incorrectly. So you get 1 point added to your score for each correct answer, and you lose a fraction of a point for every wrong answer. And I think the GRE works sort of similar to this, although actually maybe not. I think they might have actually changed the scoring recently. But yeah, this is just sort of one way a sort of standardized test can work. And so you get a raw score, right? You get a raw score once you take that test. Typically, it can be converted into a z-score based on the mean and standard deviation for that specific version of the test you took that year, right? So in other words, they'll compute a mean of everybody's score on verbal exam for the entire year, and they'll also get a standard deviation for that mean. And then, well, now how do they then interpret that? Okay, so to make the interpretation of scores easier, what happens is the SAT people then use the z-scores, right, for that year to create a new standardized set of scores with a predetermined mean and a standard deviation. It's simpler for people to work with. And this allows them to compare across versions, across years. So imagine, right, in 2016, right, in 2016, the raw SAT scores had a mean of 124 and a standard deviation of 5.5, right? And so we're going to take a person that took the test that year and say that they got a raw score of 130. What the SAT people are going to do is use that 130, the mean of 124, and the standard deviation of 5.5 to convert a z-score for this person, okay? Once they've got that z-score, they're then going to create a new distribution where raw scores have a mean of 500 and a standard deviation of 100. And they're going to convert this z-score for this person into this new distribution. And they can use this new distribution as a means of comparing across different test versions and different years, right? And it sounds a little bit complicated, but it's not that difficult to do, right? So first we need to compute the z-score for the raw SAT score. So for this version of the test, the mean was 124, the standard deviation was 5.5, and we were dealing with a person that got a raw score of 130. So we're going to take the raw score of 130 minus the mean for that year of 124 and divide that by the standard deviation, which was 5.5, right? And so if we do that, we get what? 130 minus 124 is 6. If we divide that by 5.5, we get a z-score of plus 1.09. Okay. So given that distribution, given that person's raw score, they were 1.09 standard deviations above the mean for that year. But now we need to convert that score into a standard distribution that SAT has created that has a mean of 500 and a standard deviation of 100. Again, this allows them to compare scores across years, across different test versions, right? So they say, okay, we're going to set this new mean, right, at 500 with a standard deviation of 100. They've made this up, right? You know, they've made this distribution up. 500, standard deviation of 100. We're going to convert all the z-scores to fit under this new distribution. So in other words, we're going to convert all the z-scores. In this case, we're going to convert the z-score of 1.09 to a new raw score that would have a mean of 500, that would fit into a distribution that has a mean of 500 and a standard deviation of 100. And so to calculate this, to compute this, we're going to multiply. Remember, we had a formula for this, right? This was the mean plus the z-score times the standard deviation. We talked about this earlier in the lecture. So we're going to multiply the z-score of 1.09 by the new standard deviation of 100 for all of this new SAT distribution. And then we're going to add the mean to that, which is 500, right? So we're going to go 1.09 times 100, right, plus 500. And this is going to give us a new raw score. So 1.09 times 100 is 109. So 109 plus 500 equals 609. So remember, this person got a raw score, right, a raw score of 130, right? And when converted to this new distribution, when we take, and they got a z-score of 1.09, right? When we convert that z-score into this new normal distribution that SAT has created, it's equivalent to a score of 609. So in other words, they can compute z-scores for every single year, for every single time they change the test. They can convert those z-scores into this new normal distribution with a mean of 500 and a standard deviation of 100. They can get a new raw score. In this case, we got a new raw score of 609. And they can compare across years or across test versions, right? So how about in 2012? In 2012, we could look at SAT scores. The mean for verbal was 132. The standard deviation was 6.2. And let's say we had a completely different version. So we did a test for the distribution in 2016. Now we're saying, okay, what about a person that got 130, right? Which is the same, if we go back, it's the same raw score the person A got when they took it in 2016, right? So what if a person got 130, but now the distribution is different, right? There was a group mean of 132 with a standard deviation of 6.2. We're going to find the z-score for person B, right? We're going to convert that z-score to fit into the new standardized distribution with a mean of 500 and a standard deviation of 100. And we're going to ask, who did better, person A or person B? So the logic is the same. We need to compute a z-score for person B, right? And so they got a raw score of 130 as well, but the mean of their distribution was 132. 132 divided by the standard deviation of that distribution was 6.2. Right, so let's see, 130 minus 132, that's -2. So -2 divided by 6.2, that's going to give us a z-score of minus 0.32. So given the distribution that this person came from in 2012, they also got a 130 raw score, but they performed 0.32 standard deviations below the mean for their year, right? But that's not enough now, right? Now we need to convert this z-score and fit it into the new standardized SAT distribution, right? So we're going to take the z-score, multiply that by the standard deviation for that year, which is 6.2, and then add that, we're going to take that z-score of negative 0.32, multiply that by the new standard deviation, which is 100, and add that to our new mean, which is 500, right? So negative 0.32 times 100 plus 500. Okay? And so if you do that, you're going to get, if I add it up, you're going to get 468. So let me go to the next slide. So when we take into consideration, so here's what's interesting about this. Both person A and person B got the same exact raw score when they took the SAT of 130, right? They both got the same thing. But performance was different for everybody that took the SAT that year, right? So in order to take into consideration how well person A did in comparison to person B, right, we have to take into consideration how well everybody did that took the SAT in those respective years, right? And so we can convert those raw scores into a z-score. And we can just compare the z-scores to one another, and we can say something about that. But SAT wants to make it a little bit easier. So they say, let's take those z-scores and convert them into new raw scores that come from a distribution with a mean of 500 and a standard deviation of 100. And it makes it easier to say sort of how well they did. So then we can plot them on our normal distribution. So, a raw score of 609 for person A, that's going to be somewhere over here, give or take, right? A raw score of 468, somewhere around here, right? And, we could label those, right? 609 for person B, 468, or 609 for person A, 468 for person B. So who had a better score? Well, person A clearly did, right? Even though both of these people got the same exact raw score on the SAT, when we standardize their scores and take into consideration the mean score and the variability during the years that they took the SAT, if we then convert them into a new standardized distribution, we can see that person A had did better on the SAT than person B. So given that the mean was higher and the standard deviation was lower in 2016, person A performed better in the confines, if you will, of that particular distribution. Another way of thinking about standardized distributions is this idea of grading on the curve. And so interestingly, this doesn't mean what students often think that it means, right? Students think that you just sort of add a certain number of points to everyone's score, or some students think, oh, well, I'm going to take whatever the highest score is and I'm going to sort of treat that as 100% to sort of work my way back down. But it doesn't work that way. If a professor grades on a curve, it technically means that they're forcing the grade distribution to look like a normal curve, right? So most people are going to earn a C, fewer people will earn B's and D's, and even fewer people will earn A's and F's. So the way this is done is by taking all of the raw scores, converting them into Z-scores, and then converting those Z-scores back into this normalized new distribution, right? With a mean and a standard deviation, it's going to produce a range of scores that fits in here. So think about that sort of next time you ask a professor to grade on a curve. So let's say you got 85% on all your classwork, right? And the mean of the class was 80 with a standard deviation of 12.4. So we can calculate that Z-score, right? We could take 85 minus 80, right? So the raw score of 85 minus the mean for the class of 80. We can divide that by the standard deviation of 12.4. So 85 minus 80, that's going to be 5. So 5 divided by 12.4, that's a Z-score of plus 0.40. Now, if your professor was to convert that into a standardized distribution, say with a mean of 70 and a standard deviation of 10, right? So you can treat the standard deviation as one letter grade in that sense. We can figure out what your final grade would be, right? And we can do that by multiplying the Z-score times the new standard deviation of 10, right? Because that's what we're fitting our Z-scores into a new distribution. And we can add the mean to that, the new mean that we're creating, which is 70, right? So if we do that, if we take 0.40, multiply that by the new standard deviation of 10, and add that to our new mean of 70, right? What do we get? We get, let's see, 40 times, or 0.4 times 10, that's 4, so 4 plus 70, you get 74, right? So note here that you'd be better off, obviously, if the professor didn't grade on the curve, because you would have got a B, right? 85 would have been a B, but when grading on the curve, when setting up a new distribution where the mean is 70, which is a C, the standard deviation is 10, which is a full letter grade, all of a sudden the 85 that you earned, once it gets standardized, becomes a 74, right? So typically, unless you're really, really an exceptional student, the last thing you want to have happen is for professors to grade on the curve. And I want to also point out that this process is affected by the standard deviation. So if the standard deviation was smaller, right, if the standard deviation was made to be 5 instead of 10, it would actually be easier to get a good grade. And it also works better if we lower the mean, right? So if we lower the mean from 70 to say 50, you can sort of figure that out on your own if you're interested. Then you would do better if you had a raw score of 85. Okay. So here's some practice problems I suggest from the back of the book that will help you, but you should have everything in order to be able to do the worksheet. And again, if you have any questions about how this works, bring it to class. I mean, I can answer some pretty simple questions, but I'm not going to go through this lecture again. So if you walk into class going, yeah, how do you calculate a Z-score? Like, we're not gonna do that. Between the book and this video lecture, you should have everything you need to be able to compute a Z-score. You should know everything you need to be able to find the raw score, assuming you have the Z-score, the standard deviation, and the mean. You should be able to plot scores on a normal curve, and you should be able to take raw scores from two completely different distributions, convert them to Z-scores and compare them. You should also be able to take those Z-scores and fit them into a new distribution like we were doing with the SAT scores, right? So you should have everything you need to do this. So cool. All right. See you on Tuesday.